Hello and welcome to this Royal Society videocast. I'm Wendy Barnaby and today I'll be talking to Professor Richard Ellis from the California Institute of Technology. Richard's written an article in the 350th anniversary issue of Philosophical Transactions of the Royal Society A. It's about gravitational lensing and what it helps us find out about the universe. He describes gravitational lensing as a unique probe of dark matter and dark energy. So, first of all, Richard, what is gravitational lensing?
So gravitational lensing is the bending of light by massive objects in the universe. When we look out in space, light rays are traveling through space and are constantly being deflected by material in the universe. And this is a phenomenon that was predicted by Albert Einstein and verified observationally 90 years ago. And we use it today as a tool for studying the cosmology, that is the nature of the universe on large scales.
Richard, in this 350th anniversary year of the Royal Society, do you think we could say that the idea goes back to one of the earliest fellows, Isaac Newton?
Yes, I think we could. If you read one of the articles that Newton wrote in 1704, he makes a puzzle. He writes that it's possible that light is deflected by massive objects. Unfortunately, we're not exactly sure what he meant by this puzzle, but much of the mathematics that is subsequently used to predict the deflection of light by massive objects is laid down in Newton's work.
But the idea didn't really cause a stir until 1919, when Arthur Eddington and Frank Dyson observed it from a small island. Can you tell me about that?
It's a very exciting story. Einstein, during the First World War, predicted that at the time of a solar eclipse, stars would not be in the same positions in the sky close to the limb of the sun as when the sun isn't in the way. The light has been deflected by the sun. And this is a crucial part of his theory of relativity. Sir Arthur Eddington at Cambridge, very much inspired by Einstein's work, but of course at war with Germany, himself a pacifist, decided that this was a triumphant way to verify Einstein's theory. He set out personally to make the photographic measurements to prove that at the time of the eclipse in May 1919, that light was indeed being deflected by the sun. He organized an expedition to a tiny island off the west coast of Africa called Principe, which I visited to commemorate the 90th anniversary of gravitational lensing. And there, at this spot, very remote, very poor island, he made these measurements. He reduced the data actually on the island itself and sent a telegram saying that he had measured this deflection, which he regarded as the most exciting moment of his career.
So why did it take almost until the end of the 70s before the idea took off again?
Until the late 1970s, astronomers were using photographic plates. Eddington used photographic plates in the eclipse expedition. When I began my early career, I was using photographic plates too. But then we got efficient electronic detectors of the kind that are in digital cameras today. And of course, once these were placed on our large telescopes, suddenly there were order of magnitude improvement in the efficiency. And so we were able to probe images that were much fainter. And that's when we uncovered these gravitational lensing phenomena.
Dark matter is very important when we think about gravitational lensing, and you've got an image to show us to explain that. How are the two connected?
So when we look, for example, in this image taken with the Hubble Space Telescope of a cluster of galaxies, this is a very powerful gravitational lens. What you're looking at in this image is a large number of galaxies all at the same distance, congregating together in this cluster of galaxies. But embedded within this cluster is also a large amount of dark matter, 40 or 50 times as much as the light that's shining in the stars that you can see in this image. Now, if you look at this image closely, you see a large number of distorted, highly elongated arcs, such as this very bright red feature here. And what this is a distant galaxy 3 or 4 times further away, whose light is being stretched and multiply imaged. We're seeing the light of this galaxy coming from different directions, just like an optical lens focuses light from a distant object. So this is very, very powerful because it tells us two things. Firstly, it confirms that the power of this lens is so great that there must be a large amount of dark matter in this cluster of galaxies. But also, if you think about it, it's acting as a sort of additional telescope. It's allowing us to magnify objects that are very far away and faint, and also enlarge them, just like a sort of magnifying glass, an additional magnifying glass. This means that we can see to greater distances in the universe than we would otherwise be able to. It enables us to enlarge objects so that we can study their internal properties. For example, is a remote galaxy rotating and spinning? And we can do that by harnessing this extra power of the gravitational lens, which is indeed this particular cluster.
Might gravitational lensing show us what dark matter is made of?
I think it's a real exciting possibility that gravitational lensing may reveal the properties of the dark matter itself. We think the dark matter is not the material that makes up you and me. Particle physicists tell us that there could be a weakly interacting massive particle that passes through ordinary material. But with enough resolution, we can use the magnification and the multiple images to address the question of, for example, is the dark matter smooth in its distribution, or is it lumpy on small scales? Is it granular, or is it smooth? And this will tell us what the nature of the dark matter particle is. But if you think about it, there's dark matter everywhere in the universe, and so a light ray traveling through the universe is constantly being deflected by a small amount. And what this means is that the whole sky actually is slightly distorted. It takes a little bit of getting used to. The sky is not what you think it is. Everything out there is being viewed through the shimmering of the dark matter. It's a bit like sitting at the bottom of a swimming pool and looking up. You have this dark matter between you and the sky that is slightly distorting what you see. And you have made a map of the sky. So we have used this technique, which is called weak lensing. This is the shimmering of the sky by the dark matter between us and the background galaxies, to make a statistical correction for this effect, so that we can make a map, a two-dimensional map, of where the dark matter is distributed. And we did this, my colleague Richard Massey and I made this map, two-dimensional map of the dark matter, using the Hubble Space Telescope. There's so much dark matter that it acts as a scaffolding for the ordinary stuff that shines. And so we were able to compare this dark matter map with a map of the galaxies and show that this is indeed the case. What about dark energy, which is the other focus of your paper? What is it, and how might gravitational lensing help us to understand it? Well, if dark matter wasn't enough of a problem, astronomers have come up with a second problem, which we call dark energy, and we don't really know what dark energy is. So in the late 1990s, my colleagues and I used supernovae, exploding stars, to trace the history of the expansion of the universe. So when we look back when we look to great distances in the universe, we look back in time. So astronomers are like archaeologists. They're able to trace directly the history of the universe. And what we found is that the universe is not slowing down in its expansion, as would be the case if the only ingredient was dark matter. Dark matter obeys the laws of gravity, and so as the universe expands, you would expect gravity to be slowing down the expansion, much of the way that when we throw a ball in the air, the Earth's gravity slows down the motion of that ball. But the universe isn't slowing down, it's speeding up. And this is a complete mystery. Why is the universe speeding up? Gravity is a positive force. There must be a negative force that's causing the universe to accelerate. Believe me, physicists don't know what this force is. We call it dark energy. What use is lensing in tracing dark energy? What we need to understand dark energy is better data. So if we could make a map of the dark matter, not in 2 dimensions, but in 3 dimensions at different times, then we could see how dark matter is being influenced by both gravity, bringing it closer together, dark energy, spreading it further apart. So the clustering of dark matter is a competition between the positive effect of gravity and the negative effect of dark energy. So we're trying to fund a new satellite that will allow us to make these crucial measurements that will allow us to trace how the dark matter distribution changes as the universe evolves.
Richard, thank you very much indeed.
Pleasure.
And thank you for watching. That's all from this Royal Society videocast. We hope you'll join us again.